Look up at the night sky. What do you see? A scattering of stars, maybe the faint glow of a distant planet, or the sweeping arc of the Milky Way. But beyond that familiar canvas lies something far stranger, something we can't quite grasp no matter how hard we stare. The cosmic horizon isn't just an edge, it's a frontier teeming with questions that defy our understanding. Black holes that warp time, galaxies vanishing without a trace, whispers of dimensions beyond our own. The universe is holding onto its secrets tightly, and today we're going to pry a few of them loose. Buckle up, we're diving into 25 of the most baffling, mind-bending mysteries lurking just beyond what we can see. Think about this for a second. Light from the farthest reaches of space takes billions of years to reach us, carrying stories from a time before Earth even existed. Yet, despite all that staggering distance and time, we've barely scratched the surface of what's truly out there. Somewhere in the void, entire galaxies are being torn apart by forces we can't explain. Stars are flickering out like candles in the wind, leaving behind riddles instead of answers. And then there's dark matter, this invisible, ghostly substance that holds the cosmos together, yet slips through our fingers every time we try to study it. These aren't just scientific puzzles, they're invitations to an adventure, one where every discovery leads to 10 more questions. This is why we're here. Not just to list facts, but to stand at the edge of the unknown and peer into the abyss together. Some of these mysteries might keep us guessing for centuries, others could be solved tomorrow with a single breakthrough. But that's the thrill of it. The universe isn't just old news. It's alive with enigmas, and every one of them has the power to rewrite what we think we know. So if you've ever looked up at the stars and felt that tug of curiosity, that itch to go deeper, you're in the right place. By the end of this journey, the night sky will never look the same to you again. Let's begin. Picture a cosmic tug of war where the rope is invisible but the pull is undeniable. That's dark matter, the universe's most stubborn secret. It doesn't glow, absorb, or reflect light, yet its gravitational grip shapes the fate of galaxies, bending the fabric of space itself. We know it's there because stars on the edges of galaxies orbit too fast to be held by visible matter alone, like children spinning on a merry-go-round that should fling them off, but something unseen keeps them anchored. For decades, scientists have chased shadows. The Large Hadron Collider, humanity's most powerful microscope, smashes particles together at nearly the speed of light, hoping to create a speck of dark matter in the debris. Underground labs buried beneath mountains shield delicate detectors from cosmic noise, waiting for a whisper of interaction. So far, silence. The harder we look, the more dark matter seems to toy with us like a ghost sliding through walls. Here's what makes it maddening. Dark matter outweighs ordinary matter 5-to-1. It's the scaffolding of the cosmos, the hidden architecture holding everything together, yet we've never touched it, never seen it. Some theories suggest it's made of undiscovered particles, exotic and shy. Others wonder if we've got gravity all wrong, that our equations need rewriting. But every dead end only deepens the mystery. Think of it like this. If the universe were a grand piano, dark matter would be the keys we can't press, the notes we can't hear, yet the music wouldn't exist without them. And until we crack this enigma, we're listening to the cosmos with half an ear. If dark matter is the universe's invisible anchor, dark energy is its rebellious counterpart, an enigmatic force pushing everything apart at an ever-increasing speed. Picture inflating a balloon, but instead of slowing down as it stretches, the expansion accelerates wildly, as if some unseen hand keeps pumping air into it against all logic. That's the reality of our cosmos. In the late 1990s, astronomers made a discovery that shattered expectations. Distant supernovae were dimmer than they should have been, meaning the space between us and them was stretching faster over time. Gravity, the force that literally holds galaxies together, was losing a cosmic tug of war. This revelation upended everything. Einstein himself once proposed a cosmological constant to explain a static universe, later calling it his greatest blunder. But dark energy brought the idea roaring back, a mysterious pressure embedded in the fabric of space itself, driving expansion. Here's the twist: we don't know if it's truly constant or evolving. If it strengthens over time, we could face the Big Rip, a scenario where dark energy grows so dominant it tears apart galaxies, then solar systems, and finally atoms themselves, reducing the universe to a cold, fragmented void. The irony is palpable. We've mapped the cosmic microwave background, detected gravitational waves, even photographed a black hole's shadow, yet dark energy remains a ghost in the equations. Some theories suggest it's tied to quantum fluctuations in empty space, while others propose entirely new physics. The Euclid Space Telescope, launched in 2023, is hunting for clues by mapping billions of galaxies, hoping to trace dark energy's fingerprint in the way they cluster and move. But for now, it's as if we're trying to study a hurricane by watching the leaves it scatters. Consider this: dark energy makes up roughly 68% of the universe's total energy budget. It's the majority shareholder in reality, yet we can't detect it directly, only its cosmic consequences. If gravity is the sculptor shaping the universe's structure, dark energy is the vandal relentlessly erasing its work. And the most haunting question isn't just what it is, but what it means for our ultimate fate. Will the Rip scenario play out, or will expansion gradually leave galaxies isolated, stars frozen, and the universe silent? The answer lies in the void, and it's not telling. The Milky Way seems like our cosmic home, a familiar swirl of stars we've mapped for centuries, but right behind it, hidden in plain sight, lurks something pulling entire galaxies toward it with irresistible force. Astronomers call it the Great Attractor, and for decades it was nearly impossible to study because our own galaxy's thick disk of gas, dust, and stars blocks the view, creating a blind spot known as the zone of avoidance. Imagine standing in a crowded room, trying to spot a mysterious figure whispering from behind a curtain of swirling smoke. That's the challenge scientists faced. But gravity never lies. In the 1970s, researchers noticed something bizarre. Hundreds of galaxies, including our own local group, were moving toward a single point in space at over 1 million miles per hour, far faster than cosmic expansion alone could explain. Something massive, something unseen, was yanking them off course. The Great Attractor isn't just a curiosity. It's a gravitational heartbeat thumping beneath the visible universe, bending the paths of galaxies like a hidden magnet tugging at scattered iron filings. Recent breakthroughs finally peeled back the curtain. X-ray telescopes like Erecita and Chandra pierced through the Milky Way's obscuring layers, revealing a colossal supercluster of galaxies. A sprawling metropolis of matter called the Laniakea supercluster, with the Great Attractor at its core. Here's where it gets eerie. Even Laniakea might not be the end of the story. Some data suggests an even larger structure, the Shapley supercluster, could be pulling the Great Attractor itself, like a Matryoshka doll of cosmic forces. The numbers are staggering. The Great Attractor's gravitational influence spans hundreds of millions of light years, its mass equivalent to tens of thousands of Milky Ways. Yet it's not the densest region we found, just the closest heavyweight in a universe where gravity's reach defies intuition. One theory suggests it's not a single object but a confluence of dark matter filaments, those invisible threads weaving the cosmic web. What does this mean for us? Right now, we're caught in the flow, riding a river of galaxies toward an unknown destination. But don't panic. The scale is so vast that by the time we'd get anywhere near it, the universe itself might have evolved beyond recognition. The Great Attractor isn't just a destination. It's a reminder that even the grandest structures in the cosmos play by rules we're only beginning to decipher. And somewhere beyond it, the next gravitational mystery waits, hidden behind another curtain we've yet to lift. One moment, the cosmos is silent. The next, an incomprehensible blast of energy erupts more power in a millisecond than our sun emits in 80 years, and then it's gone. Fast radio bursts, or FRBs, are the universe's most cryptic Morse code, brief flashes of radio waves that strike without warning, leaving astronomers scrambling for answers. The first was discovered in 2007, buried in archived data like a cosmic fossil, and since then we've detected hundreds more. But here's what keeps scientists up at night. Some burst once and vanish, while others repeat in erratic, unpredictable patterns, like a radio station flickering on and off at random. The leading suspect, magnetars, neutron stars with magnetic fields so intense they could strip the information from a credit card halfway across the galaxy. Imagine snapping a cosmic rubber band. When these stars' crusts crack under magnetic strain, they might release bursts of energy visible across the universe. In 2020, a magnetar in our own galaxy emitted an FRB, offering the first direct clue. But not all bursts fit this mold. Some pour out energy thousands of times brighter than any magnetar we've seen, and others repeat on schedules with no clear explanation, like a drummer lost in space. Then there's the elephant in the room. Could these be signals from intelligent life? The infamous WOW signal from 1977, a 72-second radio spike so peculiar an astronomer scrawled, "Wow." On the data printout taught us how easily cosmic noise can mimic artificial patterns, but FRBs are different. Their frequencies chirp as they travel through space, a fingerprint of their journey through the fabric of the universe, making natural origins far more likely. Still, the possibility lingers, especially for repeating bursts with odd structures, like FRB 121102, which pulses every 157 days like clockwork. What makes these bursts truly bizarre is their sheer power. One, dubbed the Lorimer burst, traveled over 3 billion light-years before reaching Earth, meaning whatever created it unleashed as much energy as 500 million suns in a blink. Some theories suggest cosmic collisions, like neutron stars merging, or even black holes evaporating in a final burst of radiation. But no single explanation fits all the data. Here's the real puzzle. If these bursts are so common, why did we only notice them 15 years ago? The answer lies in scale. The universe is vast, and catching a millisecond flash requires telescopes staring at the right patch of sky at the exact right moment. New arrays like the Canadian HI-FIB instrument now scan continuously, hunting for these ephemeral cosmic fireworks. Each discovery chips away at the mystery, but for now, fast radio bursts remain one of space's most tantalizing enigmas, brief, brilliant, and utterly bewildering. At first glance, the math seems undeniable. With hundreds of billions of stars in our galaxy alone, many hosting planets in the so-called Goldilocks zone where liquid water could exist, the universe should be teeming with life. So why does the cosmos feel so profoundly empty? This is the Fermi Paradox, the jarring contradiction between high probability of extraterrestrial civilizations and their complete absence of contact. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual lunch conversation in 1950, this question has haunted scientists for decades. Let's break down the eerie silence. The universe is roughly 13.8 billion years old, while human civilization has existed for a mere blip about 10,000 years. If even one advanced civilization arose millions of years earlier, they could have colonized the galaxy by now through slow but steady expansion. Yet our radio telescopes hear nothing but static. No interstellar probes, no alien megastructures blotting out stars, not even a single unmistakable hello from the void. Enter the Great Filter, a chilling hypothesis suggesting some catastrophic barrier prevents life from progressing to interstellar communication. The frightening twist: we don't know if we've already passed this filter, making us rare survivors, or if it still lies ahead, waiting to wipe us out. Optimists point to Earth's resilience. Life emerged relatively quickly once conditions stabilized, implying it might be common. But pessimists counter that the leap from single-celled organisms to complex life took billions of years, hinting at a bottleneck. Worse yet, some filters could be self-inflicted nuclear war, runaway AI, or ecological collapse threats we're already flirting with. Then there's the zoo hypothesis, a gentler but equally unsettling idea. Advanced civilizations might be deliberately avoiding us, treating Earth as a cosmic nature reserve or observing us like animals in a safari park. Imagine ants in a rainforest unaware of biologists taking notes. That could be us. Others propose we're simply too primitive to detect, like trying to spot a candle flame next to a supernova. Alien communication might rely on neutrino beams or quantum entanglement, technologies we can't yet comprehend. The darkest interpretation, we're alone, that life is so vanishingly rare, Earth might be the universe's only conscious audience staring into an empty theater. But until we scour every star, analyze every signal, the paradox remains unresolved, a riddle written in the silence between stars, daring us to listen harder. It was just a few scribbled digits on a printout, one line of data among thousands, but the single word scrawled beside it would echo through history. Wow. On August 15, 1977, astronomer Jerry Amon was reviewing recordings from Ohio State University's Big Ear radio telescope when he spotted a 72-second burst of radiation so intense it maxed out the equipment scale. Emerging from the constellation Sagittarius, the signal was 30 times stronger than the cosmic background noise, precisely matching the frequency band where hydrogen, the universe's most abundant element, naturally resonates, a logical choice for any civilization trying to shout into the void. Then, just as suddenly as it appeared, it vanished, never to repeat despite decades of frantic searching. This wasn't static or satellite interference. The signal's narrow frequency range ruled out most natural phenomena, and its intensity suggested a source far beyond our solar system. The Big Ear telescope's fixed position meant it could only observe any given point for 72 seconds as Earth rotated, making the signal's duration uncannily precise, as if someone had timed it to our planet's spin. Skeptics proposed comets, neutron stars, or atmospheric reflections, but none matched the data. Even the most conservative scientists admit the wow signal is the closest we've ever come to hearing an alien hello. The cultural ripple effect was immediate. SETI researchers doubled down on scanning the same patch of sky, while science fiction spun tales of fleeting cosmic contact. But the signal's afterlife is just as puzzling as its origin. In 2020, astronomers suggested a sun-like star in Sagittarius, 2,000 light-years away, might align with the signal's path, though no confirmed planets orbit it. Others argue it could have been a one-time event, like a distant civilization's lighthouse beam sweeping past Earth for a single, tantalizing moment. What lingers isn't just scientific frustration, but philosophical unease. The wow signal is a Rorschach test for our cosmic loneliness. For believers, it's proof we're not alone, a calling card from a civilization too distant or too advanced to sustain contact. For skeptics, it's a reminder of how easily the universe can mimic intelligence, a cosmic mirage. Either way, that scribbled wow on a decades-old printout remains the ultimate ink blot, daring us to decide, were we almost seen or are we still shouting into an empty room? Some stars flicker like candle flames in the wind, but then there's Tabby's star, a cosmic anomaly that doesn't just flicker. It plunges. Imagine watching a street lamp dim by 22%, then 15%, then back up, then down again in chaotic, unpredictable swings. That's what astronomers witnessed in 2015 when data from NASA's Kepler Space Telescope revealed KIC 8462852, later nicknamed Tabby's star, behaving like no other star we've ever seen. At first, scientists scrambled for mundane explanations. Could a swarm of comets, thousands at a time, be passing in front of the star, blocking its light? Possible, but the irregular dips didn't match the smooth, symmetrical shadows comets usually cast. Dust from collisions, maybe, but the star's infrared signature didn't show the expected heat glow from debris. Every conventional answer hit a wall, leaving one electrifying possibility hanging in the air. What if something artificial was causing this? Enter the Dyson sphere hypothesis, the idea that an advanced civilization might build vast energy-harvesting structures around their star, a concept physicist Freeman Dyson proposed back in 1960. These hypothetical megastructures, made up of orbiting solar panels or habitats, could block starlight in erratic patterns, just like Tabby's star. Media frenzy erupted with headlines blaring, "Alien megastructure found." But science, of course, demands cooler heads. Recent studies have chipped away at the wilder theories. Observations from the Los Cumbres Observatory showed the dimming affects some wavelengths more than others, exactly what you'd expect from fine dust particles scattering light, not solid megastructures. In 2021, the Hubble Space Telescope detected traces of circumstellar dust, further grounding the phenomenon in natural causes. Yet the mystery isn't dead. That same dust behaves oddly, with some dips lasting days, others years, and no clear orbital pattern to explain them. Here's what keeps astronomers hooked: Tabby's star isn't just an outlier. It's a masterclass in how one weird data point can force us to stretch our understanding of cosmic mechanics. Maybe it's interstellar debris from a shattered moon, or a young star still shaking off its dusty birth cloud. Or maybe, just maybe, it's something no one's thought of yet. A cosmic Rorschach test reminding us that the universe still holds cards we haven't even glimpsed. In October 2017, astronomers spotted something unprecedented, a reddish, tumbling object hurtling through our solar system at nearly 200,000 miles per hour. But this wasn't just another asteroid. Its trajectory was too extreme, its speed too great. This visitor, dubbed Oumuamua Hawaiian for Scout, was the first confirmed interstellar object ever detected passing through our cosmic neighborhood. And from the moment it appeared, nothing about it made sense. Start with its shape. Most asteroids resemble lumpy potatoes or jagged boulders, but Oumuamua was flat, like a cosmic pancake, with a length 10 times its width, defying every natural model. Then there was the kicker. As it sped away from the sun, it accelerated slightly, as if pushed by an unseen force. Comets often exhibit similar behavior when their icy surfaces vaporize, creating a jet-like thrust called outgassing. But Oumuamua showed no coma, the fuzzy halo of gas and dust typical of comets, no tail, no visible outgassing at all. Cue the controversy. Harvard astrophysicist Avi Loeb made headlines by suggesting the unimaginable. What if Oumuamua wasn't a natural object but a piece of alien technology? Perhaps a solar sail, a thin, reflective sheet propelled by starlight, or even a derelict probe. The idea wasn't entirely fringe. The object's brightness varied wildly as it tumbled, implying a highly reflective, possibly metallic surface. But the scientific backlash was swift. Critics argued that extraordinary claims require extraordinary evidence, and Oumuamua's oddities, while tantalizing, could still have natural explanations. Enter hydrogen icebergs. One leading theory proposes that Oumuamua was a chunk of frozen hydrogen, a substance so delicate it would sublimate under sunlight without leaving visible debris, explaining both the acceleration and the lack of a tail. There's just one problem. We've never observed hydrogen icebergs in space before. They're purely hypothetical, melting away long before reaching warmer regions like our solar system. Another camp suggests it was a nitrogen shard sheared off a Pluto-like exoplanet, but again, no direct evidence supports this. The truth is, Oumuamua slipped through our fingers before we could study it properly. By the time we noticed, it was already racing toward the outer solar system, too faint for even our best telescopes to track. Now it's just a speck of data and a lesson in humility. Whether it was a cosmic pancake of hydrogen, a fragment of alien engineering, or something else entirely, Oumuamua forced us to confront a sobering reality. The universe is full of surprises, and sometimes they leave before we can say hello. Today's moon is a silent, airless world, but billions of years ago, it was alive with geological drama. Here's the puzzle. Apollo astronauts brought back lunar rocks that contained traces of a magnetic field, proving our barren neighbor once had a protective shield like Earth. Yet today, the moon's magnetism is barely a whisper. How does a world with no atmosphere, no plate tectonics, and seemingly no active core generate, and then lose a magnetic field? The answer lies buried in lunar history, and it's rewriting what we thought we knew about dead worlds. Let's rewind 4.5 billion years. The newborn moon, still glowing from its violent birth in a collision between Earth and a Mars-sized object, was a molten inferno. Metals like iron sank to form a core, while lighter minerals rose to create the crust, just like on Earth. But here's where the paths diverge. Earth's core remains a churning dynamo, generating our magnetic field through the motion of liquid metal. The moon, smaller and cooling faster, should have shut down long ago. Yet Apollo samples tell a different story. Some rocks formed over 3 billion years back, locked in magnetic signatures, proving the field persisted for nearly 1 billion years after the moon's core should have frozen solid. Scientists are racing to solve this contradiction. One theory suggests core crystallization. As the moon's molten core cooled, lighter elements like sulfur rose while heavier iron sank, creating currents that briefly revived the dynamo like a dying battery sparking to life. Another idea points to massive asteroid impacts, whose colossal energy could have stirred the core temporarily, jump-starting magnetism in short bursts. There's even a wild-card proposal: tidal forces from a younger, closer Earth stretching and flexing the moon's interior like putty, generating heat through friction. Enter Artemis. NASA's upcoming missions aim to drill deeper than Apollo ever did, targeting the moon's south pole where ancient rocks may hold pristine magnetic records. The stakes: understanding how and when small planetary bodies lose their magnetic shields, could reveal why some worlds like Mars died geologically while others, like Earth, thrive. There's also a practical angle. Future lunar bases would benefit from knowing if buried resources like iron-rich deposits could be remnants of that primordial dynamo. The irony is profound. We've long seen the moon as a static museum piece, yet its rocks whisper of a fiery, dynamic past. Solving this mystery wouldn't just illuminate lunar history, it would show us how fragile planetary protection really is, and what it takes for a world to hold onto its life-giving shields. And buried in that answer might be the fate of every rocky world spinning through the cosmos. In the vast emptiness between planets, where gravity's pull is supposed to be predictable, two tiny spacecraft defied the laws of physics and left scientists scratching their heads for decades. The Pioneer 10 and 11 probes, launched in the early 1970s to explore Jupiter and Saturn, became famous for something entirely unexpected: an unexplained deceleration as they raced toward the edge of our solar system. Every time researchers crunched the numbers, the probes were slowing down just slightly more than Newton's equations said they should. This tiny discrepancy, just a fraction of a nanometer per second squared, might seem trivial, but in the precise world of astrophysics, it was like hearing a faint, persistent hum in a silent room, a signal that something fundamental was off. At first, the anomaly was brushed off as a glitch. Maybe it was fuel leaks or thruster misfires or even computational errors. But as years turned into decades and both spacecraft, now millions of miles apart, continued to exhibit the same odd behavior, the mystery deepened. Theorists scrambled. Some proposed hidden flaws in Einstein's general relativity, suggesting gravity might behave differently at extreme distances. Others whispered about dark matter's invisible tug or even undiscovered dimensions warping space-time in ways we couldn't yet measure. For a while, the Pioneer anomaly became the poster child for unknown physics, a ghost in the machinery of the cosmos. Then came the breakthrough: heat. Not from some exotic cosmic force, but from the probes themselves. Pioneer's nuclear power sources emitted warmth, and engineers realized that tiny, uneven bursts of thermal radiation, escaping more from one side of the spacecraft than the other, could act like a minuscule brake, slowing the probes just enough to explain the anomaly. By 2012, meticulous modeling confirmed it. The hum had an answer, mundane yet profound, a reminder that even the simplest things, like heat dissipation, can mimic the shadows of grander mysteries. But here's why this matters. The Pioneer anomaly wasn't just a quirky footnote. It exposed how fragile our understanding of space really is. For years, the discrepancy was small enough to ignore, yet large enough to hint at something revolutionary lurking in the data. It's a pattern we've seen before: unexplained glitches leading to paradigm shifts. Uranus's wobbly orbit revealed Neptune. Mercury's perihelion drift foreshadowed relativity. The universe loves hiding secrets in the decimal places, so while thermal radiation solved this puzzle, the larger lesson lingers. Every anomaly, no matter how small, is a crack in the foundation, a place where the cosmos whispers, "Look closer." And somewhere out there, another Pioneer anomaly is waiting, ready to nudge us toward the next leap in understanding. Because sometimes the biggest discoveries start with the tiniest inconsistencies. Black holes are cosmic shredders, or so we thought. Toss a book into one, and according to Einstein's general relativity, it's gone forever, crushed into the singularity's infinite density. But here's the problem: quantum mechanics insists information can never truly disappear. This clash between physics' two greatest theories birthed the black hole information paradox, a puzzle so profound it's made scientists question the fabric of reality itself. The story starts with Stephen Hawking's bombshell in 1974. He calculated that black holes aren't entirely black, they slowly leak energy, now called Hawking radiation. Over eons, this drip would cause the black hole to evaporate entirely, vanishing like a puddle in the sun. But if the hole disappears, what happens to the information of everything it swallowed? Quantum mechanics demands it be preserved, like a cosmic receipt for all that's fallen in. Yet Hawking's math suggested the radiation was purely random, a thermal fuzz with no ties to the original material. Poof, information erased, quantum rules broken. For decades, this paradox simmered. Then came the holographic principle, a radical idea suggesting all the information swallowed by a black hole isn't lost inside but smeared across its event horizon like a scrambled hologram. Imagine burning a library. The books seem destroyed, but if you could somehow decode the smoke's exact molecular arrangement, you might reconstruct every word. Similarly, the holographic principle claims Hawking radiation isn't random noise but a garbled message waiting to be decrypted. Skeptics countered with the firewall theory. What if the event horizon isn't a quiet threshold but a searing wall of energy that fries anything crossing it? This would preserve information by destroying the original object immediately. But it violates Einstein's prediction that falling into a black hole should feel uneventful, at least until gravity's spaghetti effect kicks in. The debate took a wild turn in 2016 when Hawking and colleagues proposed soft-hair hypothetical, zero-energy particles clinging to a black hole's edge, subtly encoding data like a celestial fingerprint. Meanwhile, cutting-edge lab experiments using sound wave, black hole analogs suggest information might escape via quantum entanglement, a process so counterintuitive it's been called teleportation by physicists. The stakes: if information can vanish, our understanding of quantum determinism, the bedrock of modern physics, collapses. But if it's preserved in some exotic form, we're staring at a universe far stranger than we dreamed. Here's the twist. Recent breakthroughs in theoretical math hint at a solution where both stories, relativity and quantum mechanics, are simultaneously true. The black hole's interior might exist in a quantum superposition, both destroyed and preserved until observed, like Schrödinger's cat scaled to cosmic proportions. It's as if the universe runs on two conflicting rulebooks and somehow makes them reconcile. For now, the paradox remains unresolved, a tug of war between the seen and the unseen, the known and the unimaginable. And somewhere in that tension lies the next revolution in physics. The cosmic microwave background is supposed to be the universe's baby picture, a near-perfect snapshot of the cosmos just 380,000 years after the Big Bang, its subtle variations revealing the seeds of all future galaxies. But when scientists stared at this map, they found something that shouldn't be there, an eerie alignment nicknamed the axis of evil, where certain cold spots in the radiation inexplicably line up with the plane of our solar system. This isn't just a quirk, it's a glitch in the cosmic matrix, a pattern so statistically unlikely that some physicists wonder if we're seeing the fingerprints of something far stranger than chance. First detected in 2005 by researchers analyzing data from NASA's WMAP satellite, the alignment defies one of cosmology's core principles, the Copernican principle, which states Earth holds no privileged position in the universe. The CMB should look roughly the same in all directions, its fluctuations random like static on an old television. Instead, the cold spots cluster along an axis that weirdly mirrors our solar system's orientation, as if the universe subtly acknowledges our existence. The odds of this happening by accident, less than 1 in 10,000. Skeptics argue it's an illusion. Maybe foreground dust in the Milky Way contaminates the data, or our telescopes have subtle calibration biases. But even after accounting for these factors, the anomaly persists. Some theorists float radical alternatives. Could the early universe have been stretched by a primordial magnetic field, leaving behind cosmic wrinkles? Others whisper about multiverse collisions, that our universe might have bumped against another during inflation, leaving a bruise in the CMB, the wildest suggestion. That we're seeing evidence of a universe before the Big Bang, imprinted like a shadow on the sky. Here's what's truly unsettling. If the axis of evil isn't a fluke, it implies the universe has a preferred direction, a cosmic north that challenges everything we know about isotropy and the uniformity of space. Imagine rolling dice and always getting sixes, not just once but consistently against all probability. That's the level of unease this discovery stirs. Future missions like the European Space Agency's Planck satellite have tried to confirm or debunk the alignment, yet the results remain tantalizingly ambiguous. The axis of evil isn't just a scientific oddity, it's a philosophical grenade. Either we've misread the universe's most sacred text, or there's a chapter we haven't even glimpsed yet. And until we crack this code, the cosmos keeps whispering a haunting question. Are we truly just spectators, or is the universe somehow watching us back? Most of the universe resembles a bustling city, galaxies clustered like skyscrapers, connected by glowing highways of gas and stars. But in the constellation Boötes, astronomers found the opposite, a sprawling void so empty it defies logic. Stretching 330 million light-years across, this cosmic desert contains fewer than 60 galaxies where standard models predict thousands. It's not just a gap, it's a staggering absence, a hole punched through the fabric of the cosmos. The discovery in 1981 was accidental. Astronomers mapping galaxy distributions kept hitting a region where their telescopes found almost nothing, as if the universe had skipped a page in its own instruction manual. What could carve such a void? One theory points to quantum fluctuations during the Big Bang. In the universe's first trillionth of a second, tiny energy ripples, like microscopic bumps in space-time, determined where matter would clump. Most areas saw dense concentrations, birthing galaxy clusters. but perhaps this void was a rare, underdense fluctuation, a bubble where space stretched too thin for stars to ignite. If true, it's a fossil from creation itself, preserved for billions of years. Then there's the multiverse angle. Some models suggest our cosmos collided with another universe during inflation, the explosive expansion right after the Big Bang. The collision could have squeezed out matter from the Boötes region like toothpaste from a tube, leaving behind this eerie vacancy. Others propose more radical ideas that the void is a scar from the death of an advanced civilization that harnessed dark energy, or even a glitch in the simulation we call reality. But here's the twist that unsettles scientists. Voids aren't supposed to be this large. Computer simulations of cosmic evolution struggle to recreate structures of this scale without tweaking the rules of physics. It's as if the universe rolled a die and landed on a number that doesn't exist. Even more perplexing, the Boötes void isn't alone. The WMAP and Planck satellites later spotted other supervoids, each challenging our grasp of cosmology's basics. For now, the void keeps its secrets. Telescopes like the Vera Rubin Observatory are scanning these emptinesses for traces of primordial radiation or distorted light that might hint at their origins. But every unanswered question circles back to the same humbling truth: the universe isn't just stranger than we imagine, it's stranger than we can imagine. And somewhere in that darkness, between the galaxies that aren't there, the next cosmic revelation might be waiting. Saturn's North Pole shouldn't exist, at least not like this. While Earth's Arctic swirls with predictable circular storms, Saturn boasts something straight out of geometry class, a near-perfect hexagon wider than two Earths, its razor-sharp edges spinning in a manic dance for decades. First spotted by Voyager in the 1980s and later studied in stunning detail by the Cassini probe, this six-sided hurricane defies every law of fluid dynamics we know. Imagine throwing water into a spinning bowl. You'd expect whirlpools, not a honeycomb pattern etched into the clouds. Yet there it sits, a cosmic stop sign hanging over Saturn's pole since at least 1981, possibly far longer. The numbers alone are staggering. Each side of the hexagon stretches nearly 8,000 miles, with winds screaming at over 300 miles per hour, faster than Earth's most violent tornadoes. But speed isn't the odd part, it's the stability. Most planetary storms churn unpredictably, like Jupiter's Great Red Spot, which shrinks and grows over centuries. Saturn's hexagon, it's locked in place like a machine part, maintaining its shape through seasons that last 7 Earth years. Cassini's infrared eyes revealed something even stranger. The hexagon isn't just surface deep. It's a towering structure plunging 60 miles into the atmosphere, with warmer layers below somehow reinforcing the colder geometry above, like a skyscraper of storm. Scientists first tried explaining it with kitchen physics. Fill a round pan with water, spin it, and smaller circular vortices can merge into polygon shapes, but only temporarily. Saturn's hexagon persists. One leading theory points to Rossby waves, giant atmospheric ripples that could theoretically stabilize edges under certain conditions. On Earth, these waves help steer jet streams, but Saturn's rapid rotation, a day lasts just 10 hours, might amplify them into geometric perfection. Another idea suggests the hexagon acts like a cosmic standing wave, where energy bounces between the planet's interior and atmosphere like sound in an organ pipe, creating nodes at precise angles. Yet these explanations hit snags. Computer simulations can't replicate the hexagon's longevity without tweaking variables to unrealistic extremes, even more baffling. The hexagon's color changes with Saturn's seasons, shifting from golden to blue as sunlight waxes and wanes, proving it's deeply tied to atmospheric chemistry we don't fully grasp. Then there's the South Pole, which hosts a circular storm with an eye eerily similar to Earth's hurricanes, as if Saturn's hemispheres followed different rulebooks. Cassini's final act added another layer. As the probe dove toward its 2017 destruction, it detected odd radio emissions from the hexagon's region, hinting at complex electromagnetic interactions beneath the clouds. Some researchers now speculate that deep inside Saturn, where metallic hydrogen swirls under crushing pressure, hidden currents might be shaping the storm from below, a hidden hand guiding the chaos. What makes the hexagon more than a curiosity is what it reveals about fluid dynamics writ large. If we can crack why this perfect shape endures, it might rewrite textbooks on everything from weather prediction to fusion energy containment. For now, though, it remains a six-sided enigma, a reminder that even the simplest geometric shapes can hold the universe's deepest secrets when painted across the skies of a gas giant. Dark matter isn't just a cosmic ingredient, it's supposed to be the glue holding galaxies together. So when astronomers stumbled upon a galaxy that seemed to lack it entirely, the discovery sent shockwaves through astrophysics. NGC 1052DF2 isn't just an oddball. It's a full-blown heretic, a spiral of stars drifting through space without the invisible scaffolding every other galaxy relies on. Found 65 million light-years away in the constellation Cetus, this ghostly galaxy is so diffuse you can practically see straight through it, its stars scattered like diamonds on black velvet. But here's what makes it impossible to ignore. When researchers measured its rotation speeds in 2018, the numbers didn't add up. Without dark matter's gravitational pull, the outer stars should have been sluggish, drifting like leaves in a breeze. Instead, they moved almost exactly as fast as the inner stars, as if the galaxy had somehow cheated the universe's rules. The implications are staggering. If dark matter is truly absent here, it challenges the very foundation of modern cosmology. One leading theory suggests DF2 might be a failed galaxy, born from gas too turbulent to form the usual dark matter halo. Others propose it suffered a catastrophic collision, stripped of its dark matter by a larger neighbor's gravity, like a tree losing its bark in a storm. But when the Hubble Space Telescope went hunting for evidence of such a violent past, it found nothing. No scars, no debris trails, just a quiet, undisturbed island of stars. This is where the plot thickens. Some physicists argue DF2 isn't an anomaly, it's proof we've been wrong about gravity all along. Enter modified Newtonian dynamics, or MUND, a controversial theory suggesting dark matter doesn't exist at all. Instead, gravity might behave differently at cosmic scales, strengthening just enough to mimic dark matter's effects. MUND has quietly lurked at the fringes of physics for decades, but DF2 is its strongest courtroom witness yet. If galaxies can exist without dark matter, maybe we've been inventing an invisible substance to patch over flawed equations, yet the skeptics aren't backing down. Follow-up studies reveal DF2's distance might be miscalculated. If it's closer than we thought, its stars would naturally orbit faster without defying physics. Another oddball galaxy, DF4, also lacks dark matter, but its stars are clumped differently, hinting at unique formation conditions. The debate rages on, with each new observation adding twists. JWST infrared eyes are now scrutinizing these galaxies, searching for faint star clusters or tidal tails that might reveal their true history. What makes DF2 more than a cosmic curiosity is what it says about scientific humility. For years, dark matter was the only answer until a single, wispy galaxy dared to whisper, "What if?" Whether it's a statistical fluke, a challenge to Einstein, or evidence of something entirely new, one thing's certain: the universe loves proving we've barely scratched the surface of its secrets. In the afterglow of the Big Bang, the cosmic microwave background paints a nearly uniform picture of the early universe, except for one glaring exception. Lurking in the constellation Eridanus, a chilling anomaly known as the CMB cold spot stretches 1.8 billion light-years across, its temperature dipping strangely lower than surrounding space. At first glance, it might resemble just another cosmic underdensity, a vast supervoid where galaxies are sparse, but the numbers tell a far stranger story. This region isn't just cold, it's too cold, defying even the most generous statistical models. When the Planck satellite mapped it in detail, researchers calculated the odds of such an extreme fluctuation occurring naturally at less than 1 in 50. Either we're witnessing the universe's most improbable dice roll, or something far more exotic is at play. One camp argues the cold spot is the imprint of a supervoid, a staggeringly empty bubble of space where matter is so scarce that photons lose energy crossing it, like marathon runners hitting an unexpected hill. But here's the catch: when astronomers surveyed the region with optical telescopes, they found nowhere near enough missing matter to explain the temperature drop. The supervoid theory requires a void so vast and empty it would dwarf the Boötes void, yet no such structure appears. This leaves physicists with two unsettling options. Either our understanding of how voids interact with the CMB is fundamentally flawed, or the cold spot isn't a void at all. Enter the multiverse hypothesis. Some theorists propose the cold spot could be a bruise from a collision with another universe during cosmic inflation, a time when space expanded exponentially faster than light. In this scenario, our infant universe might have bumped against a neighboring bubble, their mutual repulsion leaving behind a telltale cold patch in the CMB. It's a radical idea, but the math holds. Simulations show such collisions would create circular temperature anomalies with sharp edges, eerily matching the cold spot's profile. Skeptics counter that these models are speculative, requiring untested physics. Yet the Planck data added fuel to the fire. While it couldn't confirm the multiverse, it couldn't rule it out either, leaving the door cracked for wilder possibilities. The plot thickens when you consider polarization. The cold spot's light waves don't just skew colder, they're also twisted in unexpected ways, as if stretched by gravitational forces we can't see. Could this hint at primordial magnetic fields, relics from before the Big Bang? Or might it suggest dark energy isn't uniform, clustering in ways that warp space-time itself? The James Webb Space Telescope is now peering into this cosmic riddle, hunting for faint galaxies that might reveal hidden structures. What makes the cold spot more than a scientific curiosity is what it represents, a crack in the smooth facade of the early universe. Whether it's evidence of a parallel reality, a flaw in our cosmic equations, or simply a statistical ghost, one thing is certain. It's a reminder that the universe's first light still holds shadows we've yet to illuminate. Somewhere between the particles we know and the empty space we don't, there might be an invisible ingredient stirring the cosmic pot, something so strange it doesn't even behave like matter at all. Meet the unparticle, a theoretical phantom lurking in the equations of physics, not as a solid particle, not as pure energy, but as something in between. Imagine trying to hold syrup in your hands. It's not a liquid, not a solid, but something that slips through your fingers in a way you can't quite define. That's the eerie essence of unparticles. They don't fit the usual rules. They don't have a fixed mass or obey the predictable rhythms of quantum mechanics. Instead, they exist in a fuzzy, fractional state, like echoes of particles that never quite materialized. This isn't just abstract noodling. Unparticles could be the missing piece in one of cosmology's biggest puzzles, dark energy. We know the universe is expanding faster and faster, but we don't know why. If unparticles exist, they might be the hidden engine behind that acceleration, a kind of cosmic syrup oozing through space, subtly stretching it apart. The math hints at something extraordinary. Unparticles wouldn't interact with light or ordinary matter, making them invisible to telescopes, yet their push could be gentle enough to mimic dark energy's effects. It's as if the universe has been whispering its secrets in a language we're only now learning to hear. The idea was born in 2007 when physicist Howard Georgi proposed that certain high-energy theories beyond the standard model could produce unparticles as a byproduct. Picture a cosmic bakery where familiar particles like electrons and quarks are neatly shaped cookies. unparticles would be the dough that never got cut, a formless, stretchy remnant with bizarre properties. Unlike particles that clump into atoms, unparticles would exist as a diffuse haze, their energy spread unevenly across space. Some models even suggest they could remember past interactions in strange ways, like a shadow that lingers long after the light is gone. Here's where it gets weirder. Unparticles don't just challenge our understanding of matter, they rewrite the rules of gravity itself. Einstein's relativity ties gravity to the curvature of spacetime by massive objects. But unparticles might create gravity without mass, warping spacetime through pure scale-free energy. Think of it like this. Normally, dropping a rock in a pond makes ripples with clear, measurable wavelengths. Unparticles would make ripples that look the same at any scale, a disturbance without a pattern, a force without a source. Skeptics argue this is all mathematical sleight of hand, a clever idea with no experimental backing. Yet the unparticle hypothesis refuses to fade. Some researchers point to anomalies in neutron star behavior or subtle gaps in particle collision data as possible fingerprints. Others are designing tabletop experiments to hunt for unparticle-like forces using ultra-precise pendulums or lasers. The stakes couldn't be higher. If unparticles are real, they'd bridge quantum mechanics and gravity, potentially solving dark energy's riddle and opening doors to a unified theory of everything. The beauty of this idea lies in its audacity. For centuries, we've tried to categorize the universe into neat boxes, particles here, forces there. The unparticle dares us to think outside those boxes, to imagine a reality where matter isn't just what we can see or touch, but something fluid, elusive, and profoundly strange. Until we find proof, it remains a ghost in the equations, but as history shows, today's ghosts have a habit of becoming tomorrow's breakthroughs. Out beyond Neptune, where sunlight fades to a dim twilight, the Kuiper belt stretches like a cosmic junkyard, home to icy remnants left over from the solar system's birth. Astronomers expected this region to be a gradually thinning field of debris, with smaller objects scattering farther into the void. But reality had other plans. Around 50 astronomical units from the Sun, that's 50 times Earth's distance, something bizarre happens. The Kuiper belt doesn't just fade away, it plummets as if someone drew a line in the solar system and declared, nothing beyond this point. This sudden vanishing act, known as the Kuiper cliff, is one of the most perplexing boundaries in our cosmic neighborhood, and it's sparking wild theories about hidden planets, interstellar visitors, and gaps in our understanding of how planetary systems form. The first hints of this cliff emerged in the early 2000s when surveys like the Deep Ecliptic Project began cataloging Kuiper belt objects. The data revealed a steep drop-off in objects beyond 50°, far sharper than standard models predicted. It's as if the outer solar system were a construction site where workers abruptly stopped laying bricks. Some researchers initially chalked it up to observational bias. Maybe our telescopes just couldn't spot faint objects that far out. But even with advanced instruments like the Subaru telescope and Hubble, the cliff held firm. The scarcity isn't just a fluke, it's a real feature, and it demands an explanation. This is where Planet 9 enters the picture. Hypothesized in 2016 by astronomers Konstantin Batygin and Mike Brown, this undiscovered super-Earth, roughly 10 times the mass of our planet, could be lurking hundreds of miles away, its gravity carving a path of destruction. One theory suggests Planet 9's orbit might have shepherded Kuiper belt objects inward, clearing out the distant regions like a cosmic bulldozer. Computer simulations show this could work, but there's a catch. We haven't actually found Planet 9 yet. Its existence is inferred from the odd, clustered orbits of a handful of extreme trans-Neptunian objects, like a detective piecing together a culprit from scattered footprints. Until we spot it directly, the Kuiper cliff remains circumstantial evidence at best. But what if the culprit isn't a planet at all? Another tantalizing idea involves a rogue star. Billions of years ago, during the solar system's chaotic infancy, a passing star could have swung too close, yanking distant objects away like a gravitational thief in the night. This isn't as far-fetched as it sounds. Stellar flybys were far more common in the crowded early galaxy, and some astronomers argue the Sun's sibling stars might still bear the scars of such encounters. The math shows a close encounter could explain the cliff, but without a smoking gun, some telltale warp in the orbits of surviving Kuiper belt objects, this theory remains in the realm of speculation. Then there's the possibility we're overthinking it. Maybe the Kuiper cliff isn't a mystery but a clue, a fossilized relic of the solar system's formation. The leading model of planetary birth, the NICE model, suggests the giant planets migrated outward early on, scattering debris in their wake. If Jupiter and Saturn's dance flung most of the primordial material inward or outward, the Kuiper belt's edge might simply mark where the building materials ran out. But this, too, struggles to explain the abruptness of the drop-off. Nature rarely favors sharp edges. They usually hint at something unnatural, something imposed. The truth is, the Kuiper cliff forces us to confront how little we know about our own cosmic backyard. Every time we draw a boundary around the solar system, the universe redraws it. New Horizons, the spacecraft that gave us stunning views of Pluto, is now venturing into this enigmatic realm, hoping to spot distant objects that might trace the cliff's origins. Meanwhile, upcoming telescopes like the Vera Rubin Observatory will scan the skies for Planet 9 or other anomalies, turning speculation into answers. What makes this mystery so compelling isn't just the missing objects, it's what their absence implies. Whether it's a hidden world, a long-lost stellar intruder, or a cosmic accident, the Kuiper cliff is a silent challenge, a reminder that even in our own solar system, the universe keeps secrets just out of reach. And until we crack this one, the edge of our known world remains a frontier waiting to be explored. Most dying stars fade away gracefully, their final breaths forming delicate, spherical shrouds of gas, but not HD 44179, better known as the Red Rectangle Nebula. 600 light-years away in the constellation Monoceros, this celestial oddball defies expectations with its sharp, geometric elegance. Instead of the usual glowing orb, it presents an uncanny X-shape, as if etched into the cosmos by some unseen cosmic architect. The name comes from its appearance in early telescopic images, a red-tinged, nearly rectangular structure that seems too precise to be natural, yet there it glows, a cosmic riddle wrapped in dust and mystery. The secret lies in the dance of two stars locked in a deadly embrace. At the nebula's heart, a binary system, one aging red giant and its smaller, hotter companion, spins in a tight orbit, their gravitational waltz shaping the outflowing gas into that stark X. As the red giant sheds its outer layers, the smaller star's gravity funnels the material into two opposing cones, like twin fire hoses spraying into space. Our view from Earth looks straight down the barrel of this cosmic hourglass, the edges of the cones appearing as the rectangle's iconic lines. But why doesn't it look like a simple hourglass then? Here's where things get even stranger. The expelled gas doesn't flow smoothly. Instead, it's ejected in rhythmic bursts, creating stacked rings that give the nebula its stepped, almost pixelated appearance. It's as if the stars are coughing out matter in sync with their orbital rhythm, leaving behind a fossil record of their death throes. This isn't just a curiosity, it's a preview of our own sun's fate, albeit with a twist. In 5 billion years, our star too will bloat into a red giant, shedding its skin to form a planetary nebula. But without a binary partner, its farewell will likely be spherical, not geometric. The red rectangle challenges our assumptions about how stars die, proving that paired stars can sculpt their legacies into shapes far beyond the ordinary. Infrared observations reveal another layer, vast stores of complex hydrocarbons molecules like naphthalene and anthracene, the building blocks of life floating in the nebula's dusty lanes. Some scientists speculate these molecules could seed future generations of stars and planets, turning this cosmic graveyard into a nursery. The James Webb Space Telescope has even detected signatures of fullerenes, soccer ball-shaped carbon molecules that might protect fragile organic compounds in deep space. Suddenly, the red rectangle isn't just a pretty shape, it's a factory for the raw materials of life, proving that even in death, stars can set the stage for something new. But the biggest question remains unanswered. Why is the geometry so crisp? Most nebulae, even those from binary systems, show turbulent, chaotic structures. The red rectangle's near-perfect symmetry suggests an almost unreal level of stability in its ejection process, as if the stars are cooperating to build this monument. Some theorists wonder if magnetic fields, invisible threads woven through the system, might be guiding the gas into these precise forms. Others point to the possibility of a protoplanetary disk around one of the stars, acting like a stencil for the outflow. Whatever the answer, this nebula stands as a testament to the universe's flair for artistry. It's a reminder that even in the cold equations of astrophysics, there's room for beauty, and that sometimes the most profound mysteries come not from chaos but from order carved into the void. As telescopes grow sharper, the red rectangle's secrets may yet unfold, revealing how something so geometric could emerge from the swirling anarchy of stellar death. We think of the universe as a vast, visible expanse, but here's the unsettling truth. Nearly half of its ordinary matter is missing. Not dark matter, not some exotic substance, but the same protons, neutrons, and electrons that make up stars, planets, and even us. Scientists call this the missing baryon problem, and it's one of cosmology's most baffling accounting errors. When researchers tally up all the normal matter, they can see galaxies, gas clouds, cosmic dust. It adds up to barely 50% of what the Big Bang's afterglow suggests should be out there. The rest, for decades, it's been hiding in plain sight, a cosmic game of hide and seek played across billions of light years. The prime suspect, something called the warm-hot intergalactic medium, or WIM, a faint, sprawling web of ionized gas threading the space between galaxies. Picture steam rising from a street after summer rain, nearly invisible except under the right light. WIM is like that, a diffuse haze of oxygen, nitrogen, and hydrogen atoms, heated to temperatures between 10,000 and 10 million degrees. At these extremes, the gas glows too weakly in visible light to spot directly, yet it's too thin to show up clearly in X-rays. It's the universe's ultimate camouflage, blending into the background like whispers in a storm. For years, WIM was just a theory until astronomers got creative. In 2018, the Chandra X-ray Observatory caught a break. Studying a distant quasar, researchers noticed subtle dips in its light at specific wavelengths. These weren't random fluctuations, they were the fingerprints of highly ionized oxygen atoms in WIM, absorbing the quasar's glow as it passed through the cosmic web. It was like finding footprints in wet sand, indirect but undeniable. Follow-up studies using Europe's XMM Newton telescope found similar traces, suggesting WIM filaments might hold up to 40% of the universe's missing matter. But confirming WIM existence is just the start. Mapping it is like trying to trace a spiderweb with fog as your only light source. Chandra's latest trick involves stacking observations of hundreds of quasars, combining their faint absorption lines to build a statistical map of WIM distribution. Early results hint at a vast, interconnected network with denser knots near galaxy clusters, exactly where supercomputer simulations predicted. Yet even now, we've only glimpsed fragments. The rest might be hiding in even sparser regions or in forms we haven't yet imagined. Here's why this hunt matters. WIM isn't just lost matter. It's the universe's hidden plumbing, the channels through which galaxies exchange gas and grow. Without it, our models of cosmic evolution have a gaping hole. Future telescopes like Athena, launching in the 2030s, will peer deeper into these shadows with X-ray vision sharp enough to isolate WIM's faintest threads. Until then, the missing baryons remain a reminder sometimes what's invisible holds the universe together. For centuries, stargazers in desert skies or mountain peaks have witnessed a faint, ghostly glow stretching upward from the horizon just before dawn or after dusk, a shimmering pyramid of light resembling the Milky Way's softer cousin. This is the zodiacal light, a phenomenon long chalked up to sunlight reflecting off cometary dust drifting through the inner solar system. But recent discoveries have torn up that textbook explanation, revealing a far stranger truth. This ethereal glow might be the cosmic breadcrumbs of a planet we never expected, Mars. The traditional story seemed solid. Comets, those icy wanderers from the solar system's edge, shed dust as they near the sun. Over eons, this debris spreads into a vast, lens-shaped cloud along the ecliptic plane, the same path the planets follow. Sunlight bouncing off these particles creates the zodiacal light's soft radiance. Case closed, right, not quite. When NASA Juno spacecraft swung by Earth in 2013 en route to Jupiter, its star tracking cameras picked up something odd. Dust grains slamming into the probe at alarming speeds, far faster than drifting comet dust should move. The culprit, not icy visitors from the outer solar system, but something far closer to home. Enter the dust trains hypothesis. Mars, it turns out, might be hurling fistfuls of itself into space. The red planet's thin atmosphere and frequent dust storms create a perfect launch pad. When winds lift fine particles high enough, solar radiation can electrically charge them, and Mars's weak gravity, just 38% of Earth's, lets them escape entirely. These liberated grains don't drift lazily. They're catapulted into orbits that eventually spiral inward toward the sun, creating a dynamic, ever-renewing dust highway. Simulations show this process could be 10 times more efficient at feeding the zodiacal cloud than cometary debris. Suddenly, that tranquil glow isn't just ancient ice, it's the pulverized remains of Martian deserts, a celestial fingerprint of another world's restless winds. The implications rewrite solar system ecology. Mars's dust trains suggest planetary surfaces actively contribute to interplanetary material, not just comets and asteroids. It also raises questions about other worlds. Could Venus's hurricane-force winds or Mercury's sun-baked plains be flinging their own dust into the mix? Even Earth might participate. Lunar samples contain traces of terrestrial minerals, hinting our own atmosphere occasionally leaks particles into space. Yet mysteries remain. The zodiacal light's total dust volume still doesn't quite match Mars's estimated output, leaving room for other contributors. And some grains detected by Juno had compositions pointing toward Jupiter's moons, suggesting icy volcanism that might add its own seasoning to the cosmic soup. The European Space Agency's upcoming JUICE mission, set to study Jupiter's icy satellites, could shed light on this interplanetary spice trade. What makes this more than a dusty footnote is how it connects worlds. That soft glow in your twilight sky isn't just debris, it's a bridge, a testament to planets whispering to one another across the void, trading pieces of themselves in a slow, silent dance that paints the heavens with their scattered essence. And somewhere in that pyramid of light, there might just be a grain of Martian red, a visitor from another world catching the sun's rays one last time before its long journey ends. Most galaxies are messy, chaotic things, spirals with arms flung wide like whirling skirts, or ellipticals lumpy with ancient stars. But floating 600 million light-years away in the constellation Serpens, Hoag's object breaks every rule. This cosmic bullseye is a near-perfect ring of blue stars, 200,000 light-years across, encircling a golden core so precise it looks like it was drawn with celestial compasses. Discovered by astronomer Art Hoag in 1950, this oddity defies every model of how galaxies evolve. It's not a spiral, it's not an elliptical. It's a galaxy that somehow forgot to read the instruction manual, leaving astrophysicists scrambling to explain its existence. The first shock is its symmetry. Most ring galaxies form through violent collisions like the Cartwheel Galaxy, where a smaller galaxy punched through its center, sending shockwaves through the gas like ripples in a pond, triggering star formation in a perfect ring. But Hoag's object shows no signs of a collision partner. No debris, no twisted trails of stars, just an immaculate circle floating in isolation as if it sculpted itself. One theory suggests it's a barred spiral gone rogue. Its central bar destabilized over eons, flinging stars outward until only the core and a ring remained. But simulations struggle to replicate such perfection without leaving traces of the process. Then there's the core. Unlike collisional rings, where the center is a chaotic mess of newborn stars, Hoag's heart is eerily quiet, a quenched sphere of old, red stars with almost no young blue stars at all. This suggests the core stopped forming stars billions of years before the ring ignited, a staggering disconnect. How could the center retire while the outskirts partied on? Some models propose gas from the outer disk somehow avoided falling inward, starving the core while feeding the ring a galactic scale case of the edges hogging all the supplies. Others wonder if the core is a separate galaxy entirely, cannibalized long ago with the ring forming from leftover debris. But the real twist, Hoag's object isn't alone. Telescopes have since spotted dozens of similar Hoag-type galaxies, each with the same paradoxical blend of youth and age. Even weirder, some have nested rings, concentric circles like tree rings, hinting at multiple epochs of star formation. The more we find, the clearer it becomes. These aren't accidents. They're a class of their own, following rules we haven't deciphered yet. What makes Hoag's object more than a curiosity is what it reveals about galactic flexibility. We assume galaxies evolve along set paths, but here's one that carved its own. Maybe its perfect ring is a frozen moment in a billion-year dance, or evidence of a rare instability we've yet to model. Or perhaps, like a cosmic clock, it's ticking to a rhythm we can't yet hear. Until we crack its code, it stands as a silent challenge, proof that even in the well-mapped universe, perfection can be the strangest mystery of all. Black holes devour everything that crosses their event horizons, but what if the universe has cosmic fountains too? Enter white holes, the hypothetical twins of black holes, where nothing can enter and everything explodes outward. If black holes are the universe's bottomless drains, white holes would be its fire hoses, spewing matter and energy so violently that approaching them would be like trying to climb a waterfall. The math whispers they might exist, buried in the same equations that predicted black holes long before we saw one. Einstein's theory of relativity allows for them, painting white holes as time-reversed black holes, like hitting rewind on a cosmic vacuum cleaner until it becomes a geyser. The tantalizing part, white holes could be relics of the Big Bang itself, scars from the universe's violent birth. Imagine a black hole collapsing in one universe, only to rebound as a white hole in another. Some theorists even suggest that the Big Bang was a primordial white hole, erupting into existence from a singularity we'll never see. But here's the catch: white holes defy thermodynamics. Unlike black holes, which grow by gobbling entropy, white holes would somehow have to decrease entropy over time, spitting out order into the cosmos like a self-cleaning oven. Nature tends to favor mess over neatness, making white holes seem like cosmic wishful thinking. Yet the universe loves testing our assumptions. In 2026, astronomers spotted a bizarre gamma-ray burst, one that flickered like a dying star but lasted minutes instead of seconds. Some speculated it could have been a white hole flash, a brief window where a dying black hole momentarily turned inside out before vanishing. The data was inconclusive, but the idea lingers. Even if natural white holes are mathematically possible, they'd likely be catastrophically unstable, popping out of existence like soap bubbles the moment they form. That hasn't stopped science fiction or ambitious physics from running wild. Some models link white holes to wormholes, suggesting they could be gateways between distant points in spacetime. Others propose they're the secret engines behind fast radio bursts or dark energies push. But until we catch one in the act, white holes remain Schrödinger's cosmic objects, both possible and impossible, waiting for observation to tip the scales. The irony, if they're real, we might never see one. By definition, a white hole's fury would keep us at arm's length, a cosmic mirage always receding into theory. Imagine a planet untethered, no star to orbit, no dawn or dusk, just endless drifting through the interstellar night. These cosmic nomads called rogue planets are far from rare. In fact, they might outnumber stars in our galaxy by a staggering 20-to-1. Billions of these dark, wandering worlds slip unseen through the void, invisible not because they're small, many rival Jupiter in size, but because they've been cast adrift, cut loose from the warmth and light of any sun. How does a planet end up so alone? The answer lies in the chaos of youth. When star systems form, gravitational tugs of war between young planets can eject the weakest link, flinging it into the abyss like a cosmic game of pinball. Some rogue planets might have never known a star at all, collapsing directly from gas clouds too meager to ignite stellar fusion. Others could be the remnants of failed binary systems where one star vanished, leaving its planetary companion to wander. The result is a galaxy teeming with orphans, each carrying the scars of its violent birth. Here's where it gets fascinating. These planets aren't necessarily dead zones. Cut off from starlight, their surfaces would freeze into icy wastelands, but beneath the ice, tidal forces from nearby stars or radioactive decay could keep hidden oceans liquid. Take Jupiter's moon Europa, a frozen world with a subsurface sea twice the volume of Earth's oceans. Now imagine a rogue planet 10 times its size, warmed not by the sun but by the slow churn of its own core. Such a world could harbor hydrothermal vents, chemical soups, even, just maybe, life. Astronomers are racing to find these ghosts. Traditional planet hunting methods rely on spotting the wobble or dimming of stars, but rogue planets give no such clues. Instead, scientists use gravitational microlensing, waiting for a rogue's gravity to bend the light of a distant star like a magnifying glass, briefly revealing its presence. Already, projects like OGLE and ROME have uncovered candidates, including one 11 times Jupiter's mass, drifting just 20 light-years away. The implications are profound. If life can survive in the eternal dark of a rogue planet, it would redefine the boundaries of habitability. These worlds could be arcs carrying organisms between stars over billions of years. Or they might be cosmic freezers, preserving primordial life untouched by stellar radiation. Either way, the galaxy's true population isn't just the stars we see, it's the invisible multitude slipping between them, each a frozen enigma waiting to be found. The universe is expanding, that much we know, but how fast? That's where things get messy. Right now, two of science's most trusted methods for measuring cosmic expansion are giving us wildly different answers, and the gap between them is widening. This isn't just a rounding error. It's a full-blown crisis in cosmology called the Hubble tension, and it's threatening to upend everything we thought we knew about the universe's evolution. On one side, we have the cosmic microwave background, the afterglow of the Big Bang. By meticulously mapping its faint wrinkles with satellites like Planck, scientists can extrapolate how fast space should be stretching today. Their answer, 70 kilometers per second per megaparsec, meaning for every 3.3 million light-years you look deeper into space, galaxies appear to recede 70 kilometers per second faster. But then there's the other camp, the distance ladder method. Using pulsating stars called Cepheids and cataclysmic supernova as cosmic yardsticks, astronomers measure expansion directly by tracking how galaxies move. Their verdict, 73, that extra 3 might seem trivial, but in the ultra-precise world of astrophysics, it's a 5-alarm fire. The odds of this discrepancy being a fluke. Less than 1 in 100,000. So what's going on? Maybe our measurements are flawed. Perhaps Cepheids are trickier distance markers than we realized, or the CMB's light is subtly distorted by unseen dust. But after years of cross-checking, the glitches don't add up. This leaves the nuclear option, our standard model of cosmology, the finely tuned recipe of dark matter, dark energy, and ordinary stuff explaining the universe's structure might be missing an ingredient. Enter dark radiation, a hypothetical sibling of dark energy. Unlike its sluggish cousin, this would be a fast-moving, invisible particle, maybe even a previously unknown neutrino, shoving the universe apart faster than expected in its youth, leaving today's expansion out of sync with predictions. Alternatively, dark energy itself might not be constant but evolving, strengthening over time to stretch space faster now than in the past. The stakes couldn't be higher. If new physics is needed, it would mark the first crack in our cosmological framework since dark energy's discovery in the 90s. Upcoming telescopes like the Vera Rubin Observatory and ESA's Euclid are racing to settle the debate, but for now, the Hubble tension remains a glaring blind spot, a reminder that even our best cosmic maps might still be missing whole continents of understanding. From dark matter's ghostly grip to rogue planets wandering the cosmic void, these 25 mysteries aren't just puzzles, they're portals. Each one cracks open a door to a deeper understanding of reality, challenging everything we think we know. Whether it's the haunting silence of the Fermi Paradox or the hexagonal storm raging on Saturn, these enigmas prove the universe isn't just stranger than we imagine, it's stranger than we can imagine, always staying one step ahead of our best theories. What ties them together more than just curiosity? These mysteries are the friction points where science evolves, the moments when a single anomaly, like Oumuamua's unexplained acceleration or the Kuiper Belt's sudden cliff, forces us to rewrite the rules. Every time we think we've got the cosmos figured out, it throws a red rectangle nebula or a great attractor in our path, whispering, "Keep looking," and that's the beauty of it. The universe isn't a locked room waiting to be solved. It's a living, breathing riddle, constantly expanding in both size and mystery. For every question we answer, a dozen more sprout in its place. That's not frustration, that's fuel. It's what keeps astronomers awake at night, what sends probes to the edges of the solar system, and what turns casual stargazers into lifelong explorers. So here's the real takeaway. The cosmos isn't done surprising us, not even close. Whether your team, black hole information paradox, or lose sleep over the axis of evil's cosmic alignment, there's a mystery here for every kind of mind. Now it's your turn. Drop your favorite in the comments and tell us why it blows your mind. Because the next big discovery might start with a conversation, a wild idea, or someone just daring to ask, but what if? The universe is listening, and who knows, the next chapter in this story might have your name on it.